Welcome to Operating Systems Unit 11, Part 1. Today we're going to talk about main memory. So we're going to go over a little bit of background on main memory, review swapping, and discuss the difference between contiguous and non-contiguous memory allocation and how fragmentation can occur. So let's get started. A program must be brought into memory. So in order for anything to run and the CPU to access any instructions, everything must be brought into memory. So what happens is that memory may be slower than the processor, and so sometimes there's a cache that works with the CPU that stores copies of information in order to make things run quicker, because of the reason that things tend to be repetitive, people tend to be repetitive, and computer systems tend to be repetitive. And one of the roles of the operating system is to protect processes from each other's memory space. So that's an important role, is to allocate and keep processes separated in memory. So the operating system has a unit called the Memory Management Unit. And what happens is when a program turns into a process, there's a logical or virtual representation of this process. And then there is also the physical part of the process. So the logical or virtual process is just the virtual image the operating system has of the process, and then either the entire image is mapped into memory, which would be contiguous memory allocation, or only parts of the logical or virtual process are mapped into memory, which is non-contiguous memory allocation. So let's just review a little bit about swapping too. Usually, sometimes an entire process can be swapped out, or the operating system may just swap out parts of a process, which is just pages or segments of a process and not the entire process. And basically what happens is there's only so much physical space in memory, and without having to kill the process, maybe it's already partway through its execution, but it needs to wait for something, or a more important process comes along, you can put it into a backing store and swap it out, and then swap it back in, and it won't have to be restart at the beginning, where it will be able to restart where it was swapped out. So here's a visual of the difference between contiguous memory allocation and non-contiguous memory allocation. If you take a look at the image on the left, the figure on the left, you can see that we have two processes, and first we have the OS, which the operating system usually has its own area of memory for operating system work. And again, that depends on the structure. If it's a microkernel, it's going to be very small. If it's a monolithic operating system, it's going to it's going to take up a lot of memory space. And then there's free memory, which is memory that's ready to be allocated for different processes. And if you're using a contiguous memory allocation scheme, what happens is the entire logical process will get mapped into memory. And if you're using a non-contiguous, then only parts of the process will get mapped into memory. And contiguous just means it's all in one section and all together. So you can see the figure on the right. In the non-contiguous situation, P1 and P2, the entire process may be mapped into memory, but it's separated, because the idea with non-contiguous memory allocation is you don't want your process to take up memory space that it. So in contiguous memory allocation, what happens is this was an early way to manage memory, but it's also used today for very dedicated systems that have small processes, and each process has its own partition in memory that then it gets loaded. So there's no separation on the logical process, the size of the logical process to the physical process, because you just take the entire logical process and put that entire map into memory, and until you fill up all the spaces. And if you're going to, as you load processes in memory, there are different allocation schemes that can be used in order to fill the holes. Because if you think about it, if you put a process into memory, when it's finished and that memory space becomes available, then you have a hole in memory. And after a while, with all of this memory, that each process it puts into memory, it has a base, which is where it starts in memory, and a limit, which is the amount of space it's taking up in memory, and then you'll have these holes left over. So there are different schemes for allocating memory to processes when you have different sized holes. The first is first fit. That means that you would go through and find the hole, the quickest, starting from the top going down, the hole it will fit in. The first one it will fit in. Best fit means that you have to search the size of these holes that are available and find the one in which the process will fit the best in. And worst fit means you search out of all those holes that are available in memory and you put it into the largest hole. Now, why would you want to put one into the largest hole? Well, because it might be that the largest hole would leave more space for something else to be allocated, and the smallest hole is going to leave the best fit is only going to leave a sliver in which you won't be able to use that little sliver of memory for another process. So here's just an image. If you take a look at the on the left of the contiguous memory allocation, you can see that P1 has a base, that's where it begins in memory, and a limit, that's your operating system keeps track of how large that process is and how much memory space it's taking. And if you were to load a new process into memory, you would have these 3 free holes in memory where you can make a choice if the new process that's going to come in if it's going to use the best fit, it's going to fit in the one where it will fit the best, the worst fit, or just the first one that's available that it fits in. And on the left, this is non-contiguous. This would be segmentation because the sizes of the segments that go into memory are different sized. So, and this is a segmentation example. You could use the same scheme, best fit, worst fit, or first fit, in order to allocate new memory for segments. On the left, it would be allocating for the entire process, and on the right, it would be allocating memory for segments or parts of processes. So, external fragmentation and internal fragmentation. External fragmentation happens with we're going to do an example in the next video, but external fragmentation happens with segmentation or with contiguous memory allocation. When you have different size pieces of processes or segments that go into memory and you end up with all these little slivers of unallocated memory, and if you have enough slivers to answer a request for a memory request, but they're not all in one section, so you cannot put that process into memory or that segment into memory, that's external fragmentation. Internal fragmentation happens in paging, and when we get to paging examples, we will discuss it in more detail. But external fragmentation is for segmentation and contiguous memory allocation where you're using different sized pieces of memory. And internal fragmentation happens in paging, and we will be spending quite a bit of time in this class on paging. So here's just a quick little look of segmentation. You can see this on the left, segment 0 through segment 4. That represents one logical or virtual process that has been broken up into segments. And then those segments, the operating system will find holes in memory to fit those segments and put those segments into memory. And then it will put into the table the base, or the location where the segment begins, and the limit, which is the size of the segment. This is not really to scale, but you can still get an idea with the colors. So you can see at the figure on the right, there are 3 holes available that could be utilized for segments of another process. And there's some advantages and disadvantages to segmentation. The big advantage is that each segment has meaning, and so therefore you can put permissions on that particular segment and you can share segments with other processes. So this is a representation of paging, and in paging you take your logical or virtual memory and break it up into equal size pieces, and you break your physical memory into the same size, and the pages are the process and the frames are in memory. And we will discuss this in more detail in the next video and in the next unit. So take a look at this, read about paging, and we will be talking about paging a lot in the next unit, in the next units, and even in the next video. So thank you very much, and we'll be doing part 2 video very soon.